WTF. That's what radio astronomer Anna Kopinska labelled the image of an enormous, mysterious blob she first spotted in 2019. Billions of years from Earth, in the realms of deep space, it appeared like a ghostly ring of smoke, a glowing oddity of radio waves that didn't appear to match up with any known supernova remnant or galactic interaction. What in the world, in the universe, could this be? It may have been unusual, but this object was not alone. Named odd radio circles, or ORCs, the objects we have found seem to encompass everything we struggle to explain in the cosmos. 5 ORCs have been confirmed since Kopinska's first finding, and several more blobs may fit the profile. What cosmic force is so powerful that it could sculpt a ring of energy 1,000,000 light years wide, so vast it dwarfs our Milky Way by a factor of 10? Are these radio rings the relics of galactic rebirth, or the dying echoes of something we have yet to comprehend? And why haven't we found more of them? I'm Alex McColgan, and you're watching Astrum. Join me today as we attempt to unravel one of modern astronomy's greatest mysteries, and reveal the 4 leading hypotheses that could unlock the origin of these objects so odd they defy even the universe's standards. This mystery first began as a result of modern technology. Around the turn of the new millennium, technological advancements in radio astronomy drastically increased the number of known radio sources from just a few 100,000 to a couple million. For decades, nobody was able to significantly increase that number. That is, until recently. Radio astronomy was due for another upgrade, and Australia's National Science Agency, the Commonwealth Scientific and Industrial Research Organisation, oversaw the launch of the revolutionary Australian Square Kilometre Array Pathfinder Telescope, or ASCAP, one of several new radio telescopes coming online at the time. With 36 radio dishes that are each 12 metres across, what makes the Western Australia Radio Telescope special is its phased array feed, which allows it to image huge areas of the sky at once, unlike the previous generation of radio telescopes. ASCAP's field of view is an impressive 30 square degrees, the equivalent to the surface area of about 150 moons as seen from Earth. The phased array feed allows astronomers to ignore radio signals from things like satellites, which can otherwise create blind spots for radio telescope receivers. With this new generation of telescopes, radio astronomers are able to detect even faint, diffuse objects. Western Sydney University professor Ray Norris of CSIRO, later leading the original ORC discovery, predicted that the Australian Telescope's Evolutionary Map of the Universe project, or EMU, would be part of an extraordinary increase in our knowledge of radio sources across the universe. The project is named after the EMU in the sky, a constellation of dark nebulae, rather than stars, in the Milky Way galaxy, which has been recognized in Aboriginal astronomy for generations. All of the radio sources discovered up to that point by every radio telescope in the entire history of radio astronomy amounted to about 2.5 million sources, and the EMU project alone was expected to increase that total to 70 million radio sources. Keep in mind, that only represents the discoveries that were expected to come from just one of the new radio astronomy telescopes. Norris was certain that all of this new data would deliver some major surprises. And it did, much sooner than anyone expected. The EMU project looked at large areas of the sky that other telescopes had not imaged yet, and collected vast catalogues of data, so much that scientists expected they would need the help of machine learning to sift through it all. But it was in the process of browsing through some of the project's preliminary images that Kopinska, the radio astronomer who discovered ORCs, would first notice the oddly shaped radio emissions, using her old-fashioned human eyes. To me, that makes this discovery all the more special. Even with vast amounts of data and machine learning tools, this is an example of how human curiosity will always be an integral part of the scientific process. While browsing these early EMU images, Kopinska started to notice some strange shapes that she couldn't identify as any known space object. On an image of one of these odd shapes, a circle of radio emissions like a giant smoke ring floating in distant space, she wrote the label WTF, encapsulating just how baffling this was. Kopinska had never seen anything like it. After sharing her strange discovery with colleagues, a team of radio astronomers including Norris and Emil Lenk began sifting through the images, searching for more of these circular radio blobs. Lenk found a second blob just a few days after the initial discovery, and the team eventually coined the name odd radio circles. At first, they weren't even sure if these were real objects or just some kind of artifact error from the telescope, but they were able to use other telescopes to locate the ORCs, confirming that these odd radio circles were in fact real. The question that followed was, of course, what are these things? Luckily, we've been able to learn a bit more about ORCs since Kopinska first noticed one. This is an image of ORC-1 from the EMU pilot survey, a blurry, grayscale blob. But luckily, the EMU team also produced this second, colorized and enhanced image that helps to bring out the less obvious features while still maintaining the original resolution. In the color image, ORC-1 now appears as a hazy green-blue blob. Because this hazy blob is only actually visible in radio wavelengths, the color in this image had to be added in so that we can visualize it. It also helps us see more distinct features within the ORC structure. At least 1 billion light-years away in deep space, initial estimates suggested that ORC-1 may have a diameter of around 1 million light-years, but more recently, observations have indicated that it may actually be as wide as 2 million light-years across. That's 20 times the width of our own galaxy. So, we know how big ORCs can be and how distant they are, but what are they? At first, some thought these strange rings might be the remnants of a powerful supernova, but the conditions were all wrong. For one thing, we typically find supernova remnants near the galactic plane, and all of the ORCs we've identified are too far away from it. Not only that, but it appears that some of these ORCs might have galaxies in their centers, which is not something we see with supernova remnants. What's more, the scale is all wrong too. Most supernova remnants are a few dozen light years across, but these ORC rings are far, far larger. Big enough to encompass entire galaxies at their center, the ORCs we've observed so far are hundreds of thousands, up to 2 million light years across. These are not supernova remnants. ORCs must be something else. ORCs could also be something we are already familiar with, like the jets from a radio galaxy. But the vast distance, or maybe an odd angle, might obscure our ability to identify them. Since the initial discovery of ORC-1, astronomers have had the chance to observe it with additional telescopes, revealing an object that appears to be at the center of the circle that can be seen in both visible and infrared light. Using the South African Meerkat radio telescope, an array of 64 interlinked receptors, Norris and his team observed ORC-1 for 10 hours to create an image of the circle. They overlaid that on optical data from the Dark Energy Survey to reveal an elliptical galaxy in the center of the ORC. With this, they were able to estimate the central galaxy's distance from Earth at around 5 billion light years away. Not only did they find this central elliptical galaxy, but the high sensitivity image also revealed a complex inner structure of knots and arcs, with additional galaxies found at these knots. If Norris and his team were correct, and this elliptical galaxy is indeed located near the center of ORC 1, then it might have had a hand in creating this radio circle. However, it's also possible that the galaxy's location is a coincidence, as it may just be near the apparent center of the ORC, rather than the actual center. Armed with this new image and information, in their 2022 paper, Norris and his team considered 3 different origin stories for the ORC, with the data not favoring one hypothesis over another. The first possibility was that ORC 1's spherical shell was the result of a cataclysmic event in the elliptical host galaxy, like the merging of 2 supermassive black holes, for example. In this scenario, a merger of 2 supermassive black holes would send a shockwave out in all directions, accelerating electrons in the intergalactic medium. This could result in a bubble of radio emissions, which could appear to us as a circle of radio emissions with a brightened edge or ring. If this were the case, we would expect the ORC to contain a supermassive black hole or an active galactic nucleus. And not only does ORC 1 show evidence of a radio-loud galactic nucleus, like we would expect if this hypothesis were correct, but so do 2 other observed ORCs, lending further credibility to this hypothesis. The second possibility offered by Norris and his team for ORC 1's origin was that it could simply be radio jets from a radio-loud active galactic nucleus, or AGN, viewed end-on. Radio-loud AGNs are a type of galaxy that emit large amounts of energy from its nucleus in the form of 2 plasma jets, as matter falls into a supermassive black hole at their center. And as I mentioned, we already know that ANGs are present in many of the ORCs we have observed thus far. If we were to view this kind of system end-on, where the 2 jets were superimposed, it could create the appearance of what we see with ORC 1, lobes of radio emissions superimposed with a host galaxy at the center. However, we still need 3D simulations to help us work out whether or not these particular ANGs are producing radio jets, and if so, whether or not we are viewing them head-on. The third and final hypothesis for an origin story could be that the radio circle of ORC 1 is caused by what's called a starburst termination shock. In this explanation, millions of stars would have been born during a brief, intense period of star formation in the elliptical host galaxy. During this time, new stars would have been born at a rate much higher than normal, and would have lasted for just a few tens of millions of years, just a blink on the cosmic timescale. These stars would emit solar wind that expands out into space over billions of years, exciting electrons and creating a spherical radio emission bubble like what we see in ORC 1. While the team modeled this possibility in more detail than the first 2 hypotheses for the formation of ORC 1, showing mathematically how this scenario was plausible, Norris was clear that the data did not favor this explanation over the others. So while we do have several promising ideas, the origin of ORC 1 is still as mysterious as the odd radio circle itself. As each new ORC has been discovered, the only thing we seem to know for sure is that not all ORCs are created equally. After all, the name odd radio circles is meant as a descriptive name, like an umbrella term for any odd radio circle that can't be described by any existing type of object. So while all ORCs may include odd radio circles, each individual ORC may have its own unique origin story. The discovery of ORC 2 and 3, the second and third odd radio circles to be identified, didn't do much to help solve the mystery of how ORCs are created. In fact, they introduced even more questions. Seen in this grayscale image, the 2 ORCs appear to be very close to each other, nearly touching. They are roughly the same size, but on the right side of the image, ORC2 is bright and clearly ring-shaped, while ORC3, located to the left, is faint and appears more like a disc. In fact, ORC3 may not even be recognizable in the grayscale EMU image if it weren't for the light grey speckles seeming to cluster together into a circular shape right next to the more distinct ring shape of ORC2. Now take a look at this colour image of ORC2 and ORC3. The diffuse radio emission has been enhanced in red and overlaid on top of the original radio pattern in green. You can see the obscured green colour behind the red glow, where the ring shape of ORC2 is located, and to the left you can see its fainter sister circle of ORC3, only visible in diffuse red. The proximity of these ORCs would suggest that they are related somehow, but if that's the case, why do they appear so different? As much as I'd like to tell you that we've solved this curious case of ORC2 and ORC3 since their discovery, which was published in 2021, the nature of these sister ORCs remains an unsolved mystery to this day. Before moving on to the theories for ORC4's origin, I've got to mention ORC5, which was discovered in Australian Square Kilometre Array Pathfinder data in 2021. While we don't have any leading theories for ORC5 specifically, this ORC was found to have a central elliptical galaxy, like ORCs 1 and 4, and interestingly, ORC5 was the only one found to have both this central galaxy and a nearby neighbouring galaxy found at approximately the same distance from the ORC ring, which suggests these two galaxies are likely interacting gravitationally. While there may be some repeating characteristics, for every ORC we've confirmed so far, it seems that each one has their own unique qualities. Of course, as we discover and confirm more ORCs, it may be that this won't be the case in the future. But with so few ORCs and so little observational evidence, it's been difficult for scientists to nail down one theory for their origin. And that brings us to ORC4, dubbed the Cloverleaf ORC because of its irregular shape. Of course, this turned out to be another unique case. First identified in archival data from the giant meterwave radio telescope, the Cloverleaf ORC would end up being the most extensively observed and imaged odd radio circle to date, having been observed in radio, X-ray, and visible wavelengths. In this stunning image of the Cloverleaf ORC, wavelengths from several observations have been combined, with radio emission shown in red, optical wavelengths depicted in white to yellow, and X-ray emissions in blue. This ORC resides some 600 million light-years from Earth and stretches more than 325,000 light-years across, a little more than 3 times the width of our galaxy. In 2024, astronomers at the WM Keck Observatory in Hawaii detected strong fluorescent light from oxygen atoms coming from the Cloverleaf ORC, stretching across 130,000 light-years of the ORC's massive structure. This Oxygen-2 nebula of heated, compressed gas, also called shocked gas, seemed to have been created by a fast-moving explosion, according to Alison Coyle, astronomer and astrophysicist at the University of California, San Diego, who led the research team and conducted this study of ORC4. Since the Cloverleaf ORC also has a central elliptical galaxy, Coyle stated that one possible explanation was that this ORC could have been formed by a starburst termination shock event, one of the 3 possible hypotheses for the origin of ORC1. The team was able to calculate the age of the stars inside the galaxy in the Cloverleaf ORC and found that they are 6 billion years old. Using this and other data, they ran a simulation that showed how a similar structure to the Cloverleaf ORC could have been created by a starburst event that caused a high mass outflow rate. Both the radio emission sphere and this gas nebula sphere could have been blown out by the central galaxy by the shockwave of combined supernova explosions. While this is an exciting possibility, especially because of its similarities with one of the ORC-1 hypotheses, it's not the only possibility. That same year, using the European Space Agency's XMM Newton X-ray telescope, a team led by scientists at the Max Planck Institute for Extraterrestrial Physics in Germany detected diffuse X-ray emissions for the first time in an odd radio circle, coming from the Cloverleaf ORC. Based on their observations, the same team that observed the X-ray emission, led by German astrophysicists Bulbul and Chang, hypothesized that the Cloverleaf ORC may be linked to a cosmic dance between two groups of galaxies. The X-ray observations suggest that the Cloverleaf ORC could be the result of a messy merger of two galaxy groups that gravitated towards each other. This type of a galaxy merger could have created shock waves that would leave behind a gigantic bubble of radio emissions, like what we've seen in observations of this ORC. However, a lot is still unknown, and it's unclear why this set of galactic groups would produce such an ORC, while other similar galactic group mergers don't seem to leave behind the same gigantic bubble of radio emissions. As you can see, the mystery of how ORCs came to be is far from solved. In fact, it's still up for debate whether the Cloverleaf ORC is in fact an ORC at all, seeing as it is more of a diffuse cloud and lacks the telltale bright edges of radio emissions. Norris points out that similar cloverleaf-shaped radio clouds have been observed in other galaxy groups, not all of which are associated with ORCs. The key to resolving which objects are part of the ORC family and which are not is more data. Deeper radio and X-ray observations may be able to help identify more complex structures and help differentiate between actual and near ORCs. Luckily, several other candidate ORCs have been identified, and they may offer additional data for astronomers to study and compare to the already known cases. Now, instead of WTF, the side note on these strange radio emissions has a proper name: ORCs. But even though the jury is still out on how ORCs came to be, we are constantly gaining new insights from the likes of Project EMU and ASCAP. While studying EMU data from a nearby dwarf galaxy called the Small Magellanic Cloud, astronomers spotted the ghostly remains of two supernova remnants that were previously unknown to science, adding to our catalogue of celestial objects. In addition to those, another nearby supernova remnant was found by using the EMU survey in 2023, and turned out to be one of the closest supernova remnants to our Earth at just 4,200 light-years away. This supernova remnant, known as this, was found to be about 130 light-years across, and is thought to be just 13,000 years old. Not only has EMU aided in the discovery of previously unknown supernova remains, it is also paving the way for using machine learning and the power of citizen science to identify and catalogue some 4 million radio sources, which could include ORCs, as part of a project called the Radio Galaxy Zoo, EMU, or RGZ EMU. As of 2025, the project has had more than 2,000 volunteers and has helped to classify more than 92,000 sources. But the coolest part? You can join in and be part of the citizen science project yourself. To learn more, visit zooniverse.org and search for the Radio Galaxy Zoo EMU project. As our tools continue to improve, I believe that astronomers are bound to discover more ORCs, and even more objects we don't know even exist yet. We may learn not just how these radio rings formed, but we could also learn more about the life cycles of galaxies, the effects of starburst events, and how we may be able to trace gas from ancient events far outside their galaxy of origin. For now though, the mystery of the origin of these odd radio circles persists, although with several promising hypotheses. And to unravel this mystery, astronomers will have to conduct cosmic archaeology on a scale almost too big to fathom. For now though, the mystery of the origin of these odd radio circles persists, although with several promising hypotheses. And to unravel this mystery, astronomers will have to conduct cosmic archaeology on a scale almost too big to fathom. Solving the mystery of orcs isn't just about finding them in the sky, it's about analysing mountains of data, spotting subtle patterns, and testing ideas against the evidence. It might seem complex, but it's a skill set anyone can develop with the help from today's sponsor, Brilliant. Brilliant is an online learning platform that helps you become a better thinker and problem solver. They've got thousands of interactive lessons in maths, science, programming, data analysis, and AI, including some brand new courses I'm really excited to try, like mathematical thinking and reasoning with logic. Every lesson is hands-on, so you're actively developing deep understanding and critical thinking skills as you go. And since the lessons are bite-sized, it's easy to form a powerful daily learning habit in your spare time, like while you're waiting for the bus or between meetings. So whether you want to sharpen your scientific thinking or pick up an entirely new skill, why not give Brilliant a try? Scan my QR code or head to brilliant.org/Astrum to get started for free. The link is in the description. You'll also get 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as Astronauts on Patreon. A huge thank you to everyone who has signed up, and if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.